Welcome to this session on TLS for storage systems. My name is Eric Hibbard, and I will be talking to you today about TLS, not in a generic sense, but from the perspective of potential developers and designers of systems. A little bit of background on myself. I am a practicing security and privacy professional, actively involved in a wide range of standardization activities in information security, cybersecurity, and privacy, as well as an assortment of industry associations, the American Bar Association, where I get to work with the legal community, and probably more importantly, I chair the Storage Network Industry Association Security Technical Work Group, where I have some firsthand experience dealing with TLS issues as it relates to storage. This is the abstract that hopefully this is why you're here. As you can see, it's very much focused on the Transport Layer Security, or TLS, and to a lesser degree, the Datagram Transport Layer Security, or DTLS, as it's sometimes referred to. Both of these are important tools for securing communications, for storage management and data access for contemporary storage technologies. We're going to break the talk up into a few pieces here. One, I'm going to give you some background on TLS and DTLS, and this is really intended to make sure that we've sort of level set the technology and what's been going on with TLS over the years. The second piece, I will actually focus more on the sort of the storage-oriented aspects of it, and then I'll wrap up the session talking about expectations and considerations and potential requirements that may come in on the implementation side, but will definitely be issues from an operational perspective. In major segments of the talk, I will refer specifically to TLS, but in point of fact, almost everything I'll have to say about TLS will be applicable to DTLS, and where there are any deviations, I will make sure that those get pointed out. So if you hear me talking about TLS, unless you hear me say this is TLS unique or DTLS is different in this way, you can assume the two are close enough that what I'm saying applies to both. Okay, so as a starting point, let's dive into a little bit of background on TLS and DTLS. And as that starting point, it's always good to have a few terms. So I already talked about TLS and DTLS. The other term is SSL, which is the Secure Socket Layer. Hopefully these are all familiar to you. SSL has been around for quite some time, and I'll make some comments about its relationship to TLS shortly here. But for the purpose of this talk, these are really what I'm going to be focusing on. Okay, so TLS from an overview perspective, it is a protocol, or actually a suite of protocols that provide authenticated, confidentiality, and integrity protected communications between two endpoints. It's kind of a mouthful, but what that means is you set up effectively a secure tunnel that is encrypted. In other words, you can't, well, that's at least the story, right? That somebody sitting outside of the tunnel is not going to see what's flowing through it. And the endpoints know who they're speaking to, and there are mechanisms in place to ensure that if anything has been changed while it's in flight, that can be detected, and then you can essentially respond to that. So this is a client-server application kind of communication. And so what are you guarding against? Well, it's definitely eavesdropping, tampering, or message forgery. In other words, somebody's not being sort of spoofed, if you will. TLS is layered on top of a reliable transport protocol, for example, TCP, which is typically what you'll see, although there are other alternatives. And for example, the Trusted Computing Group has done some work with TLS over what would be a storage interface that wouldn't be a TCP kind of connection. And it's used to encapsulate a higher level protocol, for example, HTTP. So if you have done any sort of online banking or purchasing, most likely you've used the TLS over a TCP connection to protect HTTP as the high level protocol. Whether or not you knew that, you were using some pretty powerful tools here. There's a little bit of background, a little history. Netscape developed the original SSL. The 1.0 version never really saw the light of day. There were almost immediately some security problems were found, and so it wasn't used. However, SSL 2.0 did emerge, and in about 1995. So if you were around during that time frame, that was sort of the birth of the World Wide Web and early days in the browser wars. So having a protocol that allowed you to secure the connections was considered to be a huge improvement over where we were, if nothing else, to protect something as simple as passwords. Well, problems were found with SSL 2.0 almost immediately, and so work was undertaken, and that resulted in SSL 3.0, and that's basically where Netscape sort of ended its activities. It recognized that the technology was something that could be used in the broader internet community. So it actually worked with the Internet Engineering Task Force, or IETF as it's known, to take at a bare minimum the concepts that were developed with SSL, and to begin work on a standardized version of SSL. However, along the way, it became known as Transport Layer Security. There were enough political issues underway to make sure that it was renamed so that nobody got preferential treatment at the time. So within the IETF, there's a TLS working group, and it's been in place for many years. It's part of the IETF's security area. Specifications that come out of this working group for TLS are known as requests for comment, or RFCs. So you'll see in this talk, I'll mention several RFCs. Some of those become standards track, but in general, RFCs are considered standards, if you will. In addition to the RFCs, there's some important details that are captured in IANA, which is the Internet Assigned Numbers Authority. So for example, things like Cipher Suites and certain parameters. So if you need a registry, which TLS does, then those details are captured in IANA, and I've provided the URL. If you've never had a chance to go and look at that, you may find some of the content of interest. It is the place that you can go and get the comprehensive list of things like the Cipher Suites. There have been multiple versions of TLS. So version 1.0 came out in January of 1999. So that was the taking of the input from Netscape on SSL 3.0. This was the IETF's first version in terms of standardizing this kind of technology. Version 1.1 came out in April of 2006. This was again in response to some problems that were found in the protocol. Likewise, TLS 1.2 came out in August of 2008, yet again dealing with security issues that were deemed significant enough to warrant a new version. And most recently, TLS version 1.3 was released in August of 2018. So this is a fairly long gap of time in between version 1.2 and 1.3. And part of the reason for that is it took a significant amount of time for TLS 1.2 to really achieve any major adoption. And in fact, it was due to some very serious flaws in the previous versions that essentially forced a pretty rapid migration to TLS 1.2. So the IETF really learned a lot about how to kind of deal with that situation with 1.3. So rather than doing the specification and then waiting for developers who do a lot of the libraries, they actually work very closely with the developers, the providers of a lot of the TLS libraries. And in that process, learned quite a bit about issues and whatnot, and they modified the actual specification as the developers were developing the new versions of the code, if you will. So the very different, because 1.2, the specification was done first, and then there were attempts to basically implement it, and an assortment of problems were discovered, and that really sort of delayed the adoption because nobody really had any code they could use until a couple of years after the specification was available. There are also a bunch of other RFCs that detail extensions and Cipher Suites and best practices and just a plethora of things that you may or may not be interested in, but they are out there. So if you go to the IETF site and search on TLS and or DTLS, you will find many, many things to read. All right, so already mentioned SSL and TLS, and in the sort of the trade rags, you'll see that the two are often used interchangeably. In some cases, maybe seeing even SSL more predominantly than TLS. This is an unfortunate situation because in reality, they are not interchangeable. They are not the same thing. Technically, they're very different. But there's this long history going back to the early browser days of people sort of remember SSL, and they've been reticent to kind of change their ways. I would encourage you, when you talk about these two, to actually talk about TLS, because when you're engaging a security professional, somebody like me, and you mumble SSL, I'm going to be all over you because they are forbidden in my world. And if you say that, I'm going to immediately be checking to see if you in fact have implemented SSL as opposed to TLS. As I said before, the versions of SSL and TLS do not interoperate, and even the versions of TLS do not interoperate. There is no backwards compatibility. So when you use something like OpenSSL as your library of choice, when the version of TLS is selected, what basically happens is it then knows to manage a specific implementation, specific protocol, and they are actually different. And of course, last but not least, TLS 1.2 is essentially the contemporary version that many folks are currently using. All prior versions of TLS have significant enough vulnerabilities. They are unacceptable for most organizations. TLS 1.2 has some issues, but in general, there are mitigations for all the major issues that have been identified. But it's important to keep in mind that these older versions are problematic from a security operations standpoint. Just to give you an idea of some of the known attacks, and I won't go into detail on these. There's an RFC 7457 that goes through and describes some of these basic categories, and you may have recognized some of these. Like, for example, Poodle was something that was in the trade rags a few years ago, or crime or breach. So this is a place that you can go and actually take a look to see what kinds of attacks have been perpetrated against prior versions of TLS and even the current version of TLS 1.2. All right, so let's go a little deeper into TLS. So I said it's a protocol. Well, in actuality, it's a suite of protocols. There's essentially a couple of layers. The lowest layer is the TLS Record Protocol, and this is the layer that sits right above the Reliable Transport Protocol. So this is the layer that's interacting with TCP. This is also the layer that's responsible for dealing with the connection security. So it's doing the symmetric encryption that gets you the confidentiality. It's also handling the origin authentication, and it's also doing the integrity protection. So this is really sort of the heart and soul of TLS once it's established its connection and running. This record protocol is also used to encapsulate the higher level protocols, so HTTP. So as you can see, this is really the the core of what TLS does. However, it's not the only piece that exists. So the other layer in this suite is the TLS handshaking protocols, and of course, to make things complicated, one of the sub protocols is actually called the Handshake Protocol. This particular sub protocol is important in that it gets involved in the early setup of the TLS session. So this is where the client and the server are essentially going through authentication with certificates and trying to determine what cryptographic algorithms and keys are going to be used before you move into sort of the work that the record protocol is actually going to do. So it's got to figure out how can it set up a session? What are the parameters? What are we agreeing on so that both endpoints can actually ultimately talk? There's two additional sub protocols that are important as well. The second one is the Change Cipher Spec protocol, and it does basically what its title says. Think of this as you've gone through this negotiation. You're using asymmetric encryption in this early handshake phase, which is a fairly expensive encryption to perform. And now you've basically settled in on we're going to use this symmetric encryption. And we've got the key that both ends are going to use. Well, both endpoints got to know when they switch gears, so to speak, and start using symmetric encryption with this new key. And that's what this protocol does, is it's the signal that says, okay, do it now, boom. And the third piece is the alert protocol. So you can get an assortment of fatal and warnings in terms of errors when using TLS, and this is the part of TLS that handles those kinds of things. All right, I'm not going to go into sort of walk you through the steps, but what I wanted to show with this diagram is that now that we've kind of talked a little bit about the various pieces, you'll see at the very top, there are some elements that are effectively the TCP dialog that sort of starts things off, so that the two endpoints can basically find each other. And then from there, you move into essentially establishing the session. So, can you agree on a version and Cipher Suites and all those kinds of details? And if you manage to get through that, and then basically you move to the part where essentially what we call bulk encryption. So that's where TLS is just grinding through, doing what it does best. The setup time. So in this case, the sort of the orange colored items can take a bit of time, because this is where you've got some asymmetric encryption calculations being performed. And so if you see a sort of a hesitation when you do your online banking, so it may be going really fast and all of a sudden you're going to go access your account, and there's kind of a delay. Well, some of that comes out of this initial set of negotiations and calculations that get done. And then once that's done, then things move, relatively quickly. This is also part of where we've seen things like denial of service attacks, where one of the classic ones is, a client will initiate a connection, a TLS connection, orphan it, start another one, orphan it, start another one, orphan it. Then the server is stuck doing all these asymmetric encryption calculations while the client is just basically firing off a bunch of these. And it doesn't take a whole lot before these calculations can actually cause a problem, or the denial of service. And if you've got many clients participating, it can be almost an unrecoverable kind of scenario. This is one of the areas that TLS 1.3 has actually spent some time to try and deal with this kind of situation, where they can actually resume sessions. It's like, oh, I know you, I've talked to you before, and it may have retained some information, and it can resume, and without doing a bunch of these calculations, it picks up with the key that it had previously been using. So this is one of the kind of the cool functions of the TLS 1.3. All right, so let's talk a little bit about Cipher Suites, since I've mentioned them several times. So Cipher Suites are basically used in TLS, well, SSL as well as TLS. And for the format I'm showing you here, this applies to TLS 1.0, 1.1, and 1.2. And if you kind of go with the color coding I have here, the Cipher Suite will start off with the letters TLS and an underline, and then there'll be a key exchange algorithm, so like RSA, for example. And then there'll be an underscore with underscore, and then an encryption algorithm, and that might be like AES. It might be AES CDC, so that you know that it's an encryption algorithm and the mode of encryption that's going to be used. Or it could be GCM. And then the green is pointing out a message authentication algorithm, an HMAC, for example. And oftentimes what you'll see here is something like SHA will be listed, which stands for SHA-1, or maybe MD5, or something of that nature, okay? So this is the basic structure, and if you go and look at the IANA site, you'll see lots and lots of these Cipher Suites that, so you can sort of pick out, I want to use, AES. Well, then you can kind of look at where the encryption algorithm field is, and you can see all your sort of choices with AES. Now, it turns out that TLS 1.3 is not using this format. It does have Cipher Suites, but because they've done the IETF has done a rewrite, it's important to deal with some issues that have materialized over time with, you know, SSL3 and earlier versions of TLS. And so they've taken the opportunity to in fact do that. So as TLS 1.3 becomes more prevalent, you will begin to see sort of changes in Cipher Suites. And one of the reasons for that is none of the pre-TLS 1.3 Cipher Suites will work with TLS 1.3 and vice versa. None of the TLS 1.3 Cipher Suites will work with any of the previous versions of TLS or SSL. So it truly is a sort of a clean slate on a bunch of things like Cipher Suites. Okay, so continuing with Cipher Suites, it's important to keep in mind that there are, for each version of TLS, there is what's called a mandatory Cipher Suite. So this is the one Cipher Suite that everybody's expected to implement, clients and servers. So if you claim that you're doing TLS 1.2, then you are implementing TLS RSA with AES 128 CVC SHA. You have to take a breath of that. And if you go back to the previous slide, you can sort of parse this out. But the significance here is you can reasonably expect that Cipher Suite is going to be available to you on both the client and server end, so you can use that as the basis for the security. There's a caveat to that, but so this is the assumed sort of default kind of scenario. However, it's possible that there may be a profile that that the TLS implementation is operating against, and in that case, it may actually override the mandatory Cipher Suite, or it may diminish the value of that Cipher Suite. In other words, there's something else that may get preferential treatment. And then there are other instances where, due to sort of the threat landscape, something that's deemed as the current mandatory Cipher Suite might have a problem in it, and there's a desire to deprecate it. And in fact, we are right in the process of doing that right now, in that SHA-1 is being deprecated by the ITF, and there's already a draft RFC put together. And once that's completed, that's going to actually have an impact on the mandatory Cipher Suite for TLS 1.2. The earlier versions, if you look closely, you see they're triple DES. They're not even AES. So they're already in kind of the danger zone. All right, let's talk a little bit about digital certificates. So TLS uses X.509 version 3 public key certificates. It's kind of a mouthful. If you're interested in the specific details of what's in one of these certificates, because X.509 is actually out of the ITUT, but there is an RFC 5280 that actually has lots of very useful and important details for use by TLS, but this is where the details for these kinds of certificates are in the IETF space. The certificates use a digital signature that's typically issued by a CA, so public key infrastructure. And the whole point of the certificate is basically binding a public key. So remember, this is asymmetric encryption, so you get a public key and a private key, where you're basically binding a public key to an identity. That's the whole point of the certificate. And as a result of this, because of this binding and all the kinds of things that could happen, it turns out that the validation of these certificates is very important, because things like they could be revoked, or they could be malformed, or they could be bogus. There's lots of things that could happen. There are also multiple formats, encoding formats that can be used for these certificates, and not all implementations support all flavors of the encoding formats. There are converters that will allow you to move between most of the encoding formats, but there are a few that are preferred, and we'll get into those in a little bit, at least from a storage perspective. So I mentioned the importance of certificate validation. I'm going to walk you through some of the kinds of things that you really do need to pay attention to, from an implementer perspective, because it's really easy to say, no, it's going to be good, and you don't worry about it. And because the role these certificates play, if you get a bogus cert, you may be allowing somebody who shouldn't be allowed to get in, right? All right. So there's the first up is it actually an X.509 v3 certificate? Because it might not be. And so that's part of the validation that needs to take place. The next piece is, okay, so it's been signed, it's got a signature on it, but is it the correct kind of signature? Because a code signing signature is not the same as a signature for signing a certificate, at least in the security space. And so you actually have to make sure that the signature, which there's going to be some parameters that will describe what it's authorized to be used for. If it's been used incorrectly, then the certificate is not valid. The next piece is what we call the validity period. Pardon me. And this falls into the range of there's a first use and last use sort of timestamp. So you can issue a certificate in advance of when you need it, and it may not be valid until some sort of start date. But this validity period is how much time is the certificate good for? And going back a few years, on like, for example, a storage platform, you might actually issue a CA signed certificate that had a validity period of 10 years. Well, why would you do that? Well, because you can install it in the storage system and forget about it. Nowadays, that doesn't cut it. The recommended procedures for any CA signed certificate is not to exceed 2 years plus some time for transition. And we could very easily see that change possibly this fall down to maybe a year with some transitional time. So these validity periods have suddenly become fairly important, and it's just in the last 12 to 18 months where there's been a lot of discussion on this space. You also have to basically determine whether a certificate has been revoked. So the issuing CA, for example, there may have been a compromise, or somebody may have left, or a wide range of issues, and basically the certificate may be declared as not being valid. And so you don't want to actually permit a certificate to be used for authentication, for example, if it's not valid. You may not know why, but if you know that it's been revoked, you can't use it or shouldn't use it. Certificates are not as simple as just one sort of thing. You can actually have a chain of these. So you could actually have a chain of 25 certificates that, where one has signed one, and then it's been signed, and then it's been signed, and then it's been signed, and it's been signed. And from a validation perspective, you actually have to go and validate each and every one of the certificates in the chain. So that means from an implementation standpoint, you have to have the ability to basically walk this chain and to be able to chase the details on each and every one of these certificates. That's not a small bit of work, and it's important to be able to do that. And then I mentioned, whether something has been revoked or not. Well, you've got to be prepared to deal with the mechanisms for that, which is certificate revocation list or the online certificate status protocol, the CSP, to actually make a determination as to whether something's been revoked or not. Okay, so let's talk a little bit about DTLS. there are different versions, and DTLS 1.0 basically corresponds to TLS 1.1. DLS 1.2 corresponds to TLS 1.2. And there is a draft TLS 1.3 that will correspond to TLS 1.3. And for the most part, what we've been talking about actually applies to DTLS. Where it gets a little tricky is that unlike TLS, which can rely on TCP as a reliable transport, DTLS is using UDP. And so that means the application owns the problem with packet reordering. If any of the datagrams or packets get lost, and in some cases, taking what could be a large datagram and having to break that up to fit into small packets. All that is owned by the application, in other words, you. And there are some significant benefits for using DTLS, but one of the downsides is you've got to manage this aspect, whereas if you're using TCP, you get it all for free, so to speak. And okay, so let's talk about some storage-related issues. First off, I wanted to make you aware of SNIA has actually done some work in this space, and it actually has a TLS specification for storage. It's also known as ISO 20648. It specifies the elements to secure storage, management, and data access. The drivers for doing this specification were SNIA had SMI-S and CDMI and Swordfish and some others activities that all had dependencies on HTTPS. And it was recognized that there's a need to basically change the TLS over time to deal with the threat landscape. So all of that language was teased out of these specifications, localized, update, harmonized, and over time adjusted. And we've just recently done an adjustment to this. And just as soon as we got done with that, and prior to updating the ISO spec, we need to do yet another update because of some changes that's coming into place. So this is one of those activities that if you are part of the Storage Network Industry Association and you have an interest in TLS, I would encourage you to get involved with the Security Technical Work Group, because you can actually get some hands-on on how to deal with, for example, a profile, which effectively is what this is. And not only is there's all these desires to sort of harmonize the use of TLS within the SNIA specs, but also to make sure that there's a high degree of interoperability and as strong a security as possible can be achieved. And that's really some of the drivers behind doing our own profile. There's also been efforts to coordinate with other groups, non-storage activities, to try and make sure that this specification is compatible, because it's not uncommon to have, for example, key management needs where you might use the OASIS Key Management Interoperability Protocol, which is also layered on top of TLS, and what you'd hate to have is a situation where you're using CDMI for some piece of storage management, and then KMIP for key management access, and it demands two different flavors of TLS. And so, quite a bit of work has been done to coordinate with various groups to prevent that kind of problem. All right, so I'm going to walk you through some things that you should pay really close attention to if you are an implementer of TLS in a product, all right? So first up, if you have different versions supported, so in many cases, you're not going to write your own TLS implementation, just due to the complexities. You're going to probably pick one that's available and use it, which means you then have the problem of configuring it. And maybe exposing how you configure it to your customer base. We'll talk about that in a little bit. But at a bare minimum, your configuration, your default configuration, should enable and make preference, the primary preference of TLS 1.2 as the version. Absolutely disable all flavors of SSL and TLS 1.0 and 1.1 out of the chute. From a crypto perspective, In many cases, the interfaces that you'll deal with aren't at the Cipher Suite level. You'll be able to say, no null, no anonymous, no export. And again, what you're seeing here is by default, those should be disabled. Think of those sort of three categories in the Cipher Suite. You could actually have null, null, null. In other words, I have negotiated a TLS connection that has absolutely no protections whatsoever. That's what that would mean. So you want to make sure that that kind of stuff is actually disabled. There's also some encryption that is a little long in the tooth and not trustworthy. So absolutely default RC2, RC4, DES, and triple DES by default. Also, in the case of hashing functions, you want to disable MD5 and most likely SHA-1 or SHA as it's here. That gets you into the problem of with TLS 1.2. Now you've disabled the mandatory Cipher Suite. So this is where you probably need to have an additional Cipher Suite, and the recommendation is to go with what's listed here, which is TLS RSA with AES 128 CVC SHA 256. So it's the SHA 256 that's different than the mandatory. A few other things to pay attention to. If there's a separate hashing used for signatures and whatnot, and you want to make sure you're using SHA 256 or greater. And the way to do that is you actually have to use an extension called supported signature algorithms, and that's where you specify that. Well, it turns out that nothing before TLS 1.2 has the support, so you end up being locked in either on MD5 or SHA-1. So as you can see, those two being unacceptable, you may have a problem. So this is one of those fixes for TLS 1.2 that allows an adjustment, sort of behind the scenes to deal with this. With regard to the CA certificates, again, you need to be able to install the certificates into the product, and you may need to actually load certain information into trust stores so that certificates will automatically be trusted. And of course, you've got to control, how are you going to do the verification that the certificate hasn't been revoked, and in some cases you may want to put a limit on how far down the certificate chain you'll traverse. A lot of people sort of cut off chasing the chain down to a level of about 20 or 25. Okay, some other things to worry about. There's definitely been an attack against renegotiation within TLS 1.2. There's a couple of mitigations for dealing with this. One is just to flat out disable renegotiations. The other one is to actually implement an extension, which is the TLS renegotiation, the indication extension. What I've typically seen is people just disable renegotiation, and that takes care of the problem. But it was significant enough that this kind of issue was definitely addressed in TLS 1.3. TLS supports the use of compression. Again, due to some previous attacks, this should be disabled by default. And then from the encodings that the certificates use, you definitely want to support the binary distinguished encoding rules, or DER, and the base 64, which is an ASCII-based DER encoding. Both of those will give you pretty good coverage, and there are converters from most of the other encoding representations into one or both of these. All right, another problem that that exists, and various storage vendors have approached this in a variety of ways, but it's basically, if you're going to use a CA signed certificate, you have to basically produce a certificate signing request, or CSR. This requires that you essentially generate a key pair, basically a secret or private key and a public key And then that has to be combined with some information on the applicant. For example, maybe it's the storage system and the public key of the applicant. And that detail is combined, fed into CA, which then basically spits out the certificate on the other side. So having mechanisms in place that let you deal with the CSR, as opposed to basically telling a customer, download OpenSSL and run this to get your key pair, is a smart thing to do, and it makes you look a little more professional than doing what I just described. All right, so let's talk about a few expectations and considerations. So interoperability is definitely an issue. There are lots of moving parts in TLS, and it's not too difficult to get into a situation where you can't actually negotiate a connection. This is where these mandatory Cipher Suites and if there's a profile where they're basically saying you shall implement these, this is focused on how you avoid this kind of a problem. Clearly, you want to have the most secure option available, and part of the way you do that is on the client side, which starts the dialogue, is you want it to offer up in a list the most preferred, and most preferred being the most secure that the client will speak. And the server will pick from that list, and typically it will start with the first one and move down. There's no law that says it has to do that, but that's the sort of the protocol for doing something of this nature. Do keep in mind that when you're looking at the protocol that's going to be encapsulated inside of TLS, it may have some restrictions, it may have some dependencies. And I mentioned earlier KMIP. So KMIP has its own expectations as to how TLS 1.2, for example, is going to be used, and specifically what Cipher Suite should be used. So do be aware of, if you've got multiple protocols that are going to be encapsulated, that you understand all the issues and implications. Likewise, I already mentioned 20648, or the SNIA, basically TLS protocol. It's also important to know that NIST has one. So Special Publication 862 Revision 1, which was revised about a year ago, has some very specific requirements that, for example, if you implemented just what the SNIA spec said, you would actually not comply with what NIST needs. So it's, you need to be keeping an eye on some of these profiles if you're going to operate, for example, in the US government. You need to worry about crypto agility. And this is where the threat landscape is changing, new attacks are occurring, and there's a need to make adjustments. Sometimes it's just disallowing or allowing certain capabilities. It's also a reason for, as soon as a new version of TLS is available, that you should embrace it and begin, have the ability to support and choose as soon as possible, because at almost any moment, it's possible that you could actually have something that kills off the version of TLS that you're using. Certificate considerations, you want to make sure that all of the aspects of the certificates are basically 112 bits of security strength, and that's the various signing mechanisms and whatnot. We already talked about the validity period of no more than 2 years, but possibly as short as 1 year. So this is one of those things you want to be able to deal with. This is clearly an operational issue, but it may be in the implementation you're going to need to kind of help out with that. Last point here is don't use self-signed certificate. This is something that's, for years was practiced when you're dealing with systems that are isolated, but the IETF has developed Cipher Suites for pre-shared keys, and that's what's really required for those kinds of environments. So use them. Self-signed certs, there's essentially very little trust there, and you're kind of asking for trouble if you're using them. Security scans. All right, so TLS is one of those things that is absolutely going to be scanned to death. It's going to be spotted, it's going to be looked at, and anything that is enabled, if it's weak or disallowed, you will be flagged as having a vulnerability, and security professionals will, in many cases, not let you connect the product to to their networks. And this can be a very big deal for like financial institutions and governments and whatnot. So remember that list of disable these by default. That's part of the reason. Any of those show up, you're pretty much dead. And you will get to go rework that before they'll let you connect. All right, a few comments about TLS 1.3 before wrapping up here. As I said, it's the first major rewrite. It's definitely been modernized. It's getting rid of a lot of old crypto algorithm baggage. So just there's a bunch of stuff that's just not going to be available in TLS 1.3. The good news is much lighter weight. It's the reduced latency. It's going to take less resources, computational resources to use. Lots of interesting little tricks. I mentioned one about resuming sessions and whatnot. The good news is all of the certificates and keys that are typically used by TLS 1.2 are going to be compatible with TLS 1.3. And last but not least, you should anticipate there's going to be a black swan event at some point that's going to cause a rapid migration to TLS 1.3. So be ready. In other words, don't get caught flat-footed, then you've got to scramble and implement TLS 1.3. Do it early. It's out, code is readily available, and your product should be able to use it. So with that, I want to thank you for your time. And if you enjoyed this session or you thought that you had some useful details, please give us feedback. And thank you very much.